All right. Good afternoon, everybody. Can you all see me and hear me?
Yep.
All right. Thank you. All right. So first, I'd like to go over what we did last time and then take it from there. So let me quickly go over what we talked about last lecture. So last time we talked about like a brief introduction to the problem formulation of optimal control and the relationship between or the different types of optimization um, um, and basically let me go to the definition here. One second. Yeah, so this is the formal definition of the optimal control problem. So consider a dynamical system given by a differential equation of this form. We are assuming that the differential equation is nonlinear. We assume that the system has initial conditions and these initial conditions are known. And X is the state of the system. And by the state here, we mean the variables that describe the evolution of the system. And F is a continuously differentiable function. U is the input or the decision that needs to be made to control the system. And U can be constrained within a set, omega. This set is a subset of the domain of real numbers. M here, small m, is the dimension of this vector u. So we're dealing with vector valued signals and functions. And we are also dealing with a confined time domain. U can be piecewise continuous. So meaning that it's continuous everywhere except possibly at finite number of points. Um, um, so this is the setup, okay? And we're assuming obviously that the system is controllable. So the problem is find u such that the state of the system is steered from an initial state to an admissible final state subject to constraints. These constraints not only uh, 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 are related to the state, but also the constraint can also be applied to the input u, such that, and this is the most important distinguishing factor here, which is such that the cost function here, defined by this function here, it's a function of the final state plus the integration from 0 to t0 to t1, another function of the state input and time, is minimized, right? And L and phi here, these functions are we choose them. Okay, so these are subject to design. All right, so this is the formal definition of the optimal control problem, and we are going to study in this course different techniques to solve this problem. And most of these techniques are going to assume that we know the mathematical equation of the system, the mathematical model, and hence we're going to use an analytical method to solve this problem. Okay. Uh, um, uh, yeah, but as I mentioned last time, this problem is a cousin to what is now known as reinforcement learning or AI, because essentially there are uh, three things or three languages that try to express the same thing or try to address the same problem that I just mentioned. Optimal control is one of them, which again is uses like principles that we will cover in this course, but also then there is this what we call dynamic programming, which is how to find that U that will solve the problem, like in a practical sense, and then reinforcement learning, which is another way to solve the problem from data, not based on differentiation of the mathematical equation, but from data. Hopefully, I'll try to talk more about reinforcement learning towards the end of the course. But the objective of this course is to give you guys the theory, the basic theory that explains how we define these problems and how we solve them from first principles. This is the main idea. All right, so I gave a couple of motivating uh, examples. Now, there are to solve the optimization problem, as I mentioned, there are we can come up with two approaches. One is what we call trajectory optimization. So basically, this is a plan first and then control later, which means that first we need to compute the optimal open loop signal U star and the state X star, the optimal state for a given start and goal. So basically, we define an optimal control problem and we solve for trajectories. For here is the optimal controller, the trajectory for optimal controller, that if you would apply it to the system, it will give you this optimal state, right? This is offline. Okay, this is done offline, and then you take that and you solve another tracking control problem, right? So then you where you want to drive the error between U and U star to zero, right? Which means that you now make you force the system, both the U and X of the system, to follow U star and the optimal U star and X star. We call this trajectory optimization method. Another one is what we call policy learning, which is basically you learn the action, you or the mapping from data, either through reinforcement learning or imitation learning. And it produces a fast closed loop controller at inference time. Um, so, so for trajectory optimization, given a model, right, you need to minimize or optimize the cost function with respect to U, such that the dynamics of the system are respected. And there are two common approaches for this. One is called indirect, the Pontryagin maximum principle, and also there is another method that is direct using nonlinear programming. But as I mentioned, the output of this is X star and U star. And then once you have X star and U star, you have the option whether to apply U star directly to the system in a feed forward way, or solve a tracking problem. Um, the other one is policy learning, either through imitation learning, where you learn from expert demonstrations. So, for example, you take a model predictive controller as a teacher to learn from, or reinforcement learning, which is based on learning by the interaction between the controller and the system in a direct way. The output of this is policy. All right, so this is like a planning versus learning, some trade-offs. The main trade-off, the main requirement is that trajectory optimization, you need a model. For policy reinforcement learning, you don't need a model, right? But on the other side, trajectory optimization, if you have a model, you don't need a lot of data. But if you don't have a model, you need a lot of data. Okay, so this is the trade-off that you need to be aware of. Another one is that uh, uh, enforcing constraints when you have a model is easier to do than when you don't have a model. Okay, so for reinforcement learning, enforcing constraints and safety is a harder problem to solve. For real-time execution, it's harder for trajectory optimization because it's computationally hungry. It's easier for reinforcement learning. um, Generalization, you know, it depends for the trajectory optimization. Policy learning, I mean, the practical results show that one can uh, design a reinforcement learning controller to be generalizable over different environments and different sets. So you teach it on one set of data. There are some techniques that you can make it generalizable, the controller to be generalizable. Now, the interpretability, which is so interpretability has different definitions for different contexts, but basically, uh, uh, one definition is how the controller came up with a decision, right? How the decision was made, right? Obviously, if you have the model, you can trace the mathematics, and this is one of the things what we will learn in this course. You will see through the mathematics how u is obtained, how the optimal controller or the optimal decision is obtained, right? So that makes the controller interpretable. Okay, another one is stability. We can prove stability, right, in a easier way, uh, or relatively easy compared to the reinforcement learning. Okay, uh, so understanding how the controller works, right? This is what, at least my understanding of, or my definition of interpretability is that understanding how the controller works, right? Is more clear. It's clearer for trajectory optimization than for policy learning, and coming up with performance guarantees um, can be um, um, practical in trajectory optimization more than that in policy learning. But the problem, again, here, you have to take that with a grain of salt, because all depends for trajectory optimization. It depends on the fidelity and the accuracy of the model. If the model is rubbish and your control design is not robust, then you have to be careful with taking the when considering the guarantees, the stability and performance guarantees. So, and there is the notion of global versus local stability comes into play in that case. I'll talk about that a little bit during the course also. But this is basically the comparison and the trade-offs between reinforcement learning, data-driven control, and trajectory optimization. All right. Any question up to this point? Any question? Yeah. All right. So this is um, kind of a uh, figure that shows the different types of model-based, model-free control. So this is just an intro, just give you a glimpse of the types of control that are considered optimal controllers. Um, So for example, here the trajectory optimization, you need the dynamics model. Based on that, you come up with optimizer that gives you the x hat and u hat. Sorry, x star and u star, the optimal u and the optimal x, right? You take that and then you feed that to the tracker, either LQR or model predictive control, linear quadratic regulator or model predictive control, right? The tracker then forces the plant to follow X star and U star. This is one of the traditional ways of solving optimal control in real life. For policy learning, you have the plant environment, and so that gives you the experience or the data, right? and uh, based on that, you update theta, uh, 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 and you take the policy, apply it to the system, measure the data, and um, solve the optimization problem or the reward function, come up with U, and so on. So this is a reinforcement learning. So when should you use which approach? Trajectory optimization or model predictive control. Um, you should consider it when safety and constraints are central, when you have a reasonably accurate model, and when you want reliable, interpretable behavior. You should use reinforcement learning when modeling is hard. Think about a self-driven car. Think about humanoid robots, right? Uh, you know, uh, coming up with mathematical models for these systems is hard. So in that case, the obvious choice should be reinforcement learning, and perception is complex. Again, so when you have the environment, the system evolves in an environment that has images, vision, high dimensional inputs. Then reinforcement learning again can be a more suitable option. And when you need very fast reactive behavior, okay, that is not actually computationally hungry, then maybe reinforcement learning also can be a good choice. There's also hybrid approaches where you learn models and the cost or residuals, and then you plan optimize with constraints. And there are also an option of system identification approach where you or you combine neural networks with model predictive control is a hybrid option, or there is a Koopman. There is also another emerging technique called Koopman modeling, where you come up with a linear model of a nonlinear system using data, and then you take that and then you solve a model predictive control or an LQR control based on that model. So there are hybrid approaches that one can also consider. Okay. So here are some examples. Let's think about these as a group here. So let's start with the first one. So let's say you have a car in a highway lane change with strict safety constraints. So you want to design a self-driven um, uh, uh, autopilot controller for a car, right? That can decide when to change lanes in a highway with strict safety constraints. So, what do you think? Which approach should you follow here? Reinforcement learning or MPC? Anybody?
Probably reinforcement learning.
Okay.
Lots of dimensions in that one.
Yes. So in that one, if you are using like vision-based approach, which is basically it depends on the data, right, and type of data. Um, my answer would be it could be both. You could also use MPC because MPC can deal with strict safety constraints. The problem with the enforcement learning for this application is how you deal with strict safety constraints. It's a challenging problem, but you know, many examples you could use both. But reinforcement learning is because of the vision-based approach is probably the first choice. Agile drone racing with unknown wind disturbances. What do you think, guys?
Reinforcement learning.
Okay. Reinforcement learning, I think, is also another choice here. Um, Third one is biped robot walking with intermittent contacts. This is again the humanoid robots, right? I mentioned, I think, earlier that these are typical examples where reinforcement learning also can make a difference, right? So you can see that these examples, the first three examples are, if we have a mathematical model for any of these three examples, especially the first one, um, right? I would go with trajectory optimization or the optimal controller, but if not, reinforcement learning is going to be my choice. The fourth one is HVAC control, heating, ventilation, air conditioning control for a building that is energy optimal, right? And that is a classical optimal control problem. And there are, if you do a research, you'll see many results that address this point. That said, you can also use the reinforcement learning to address this problem as well. So uh, uh, choosing which controller to consider, in my opinion, right, comes to looking at the mathematical model. Is there a credible, uh, accurate, reasonably accurate mathematical model that describes the problem? Or can I work on it? Can I develop a reasonably accurate model that describes the problem? If the answer is yes, then there is value in considering optimal control because of the safety constraints, because of the interpretability, because of the advantages and the trade-offs that I mentioned in this table here. Okay, if that's not easy, then reinforcement learning would be the alternative approach. Any question? Right, let me now shift to lecture 2. So I uploaded lecture 2 in Canvas today. All right, do you see lecture 2, guys?
Yep.
Okay, so today I would like to start with a baby step number 1, I would say, which is static finite dimensional optimization. So we're not going to talk about controller yet, okay? What we're going to talk about here is how to define whether a system or a function has a minimum or a maximum point, and how can we describe it and how can we find it. Okay, so we call that static optimization. This topic you should be familiar with that. I think it's covered actually in high school, finding the minimum and maximum points of a function. The only thing that I'm going to so you can consider this as a refreshment, but also I'm going to emphasize the fact that we're dealing with vector spaces, right? So the only difference here in what I'm going to show and what I'm going to talk about here is the fact that we are dealing with vector valued functions and vector spaces. Okay, that's the key here. So this is preliminaries. So I'm going to first let's first agree on the definition of minimum and maximum points. So this stuff is in the textbook by Athens and Falb, sections 5.2 to 5.4. Please read it. All right, so let f of x be a scalar function of a single variable, right? So by scalar function, I mean its dimension is 1, right? So it takes in a variable x as an argument of a dimension 1 of real numbers, and it spits out, it gives me, it outputs, the output of this, the range of this is a value that is of dimension 1, okay? Where R is the real line in this case because it's dimension 1 from minus infinity to infinity, right? So we're in this slide, we're not talking about vectors, we're talking about scalars, dimension 1, okay? So definition, X star belongs to R is a local minimum if there is epsilon larger than 0 such that f of X star less than or equal to f of X, meaning that the value of the function at X star, right, is less than or equal to the value of the function at any other X, right? For all X minus X star is less than epsilon. The magnitude between X and X star is less than epsilon, meaning that for all X that are locally near X star. So as long as we are near X star, right, the value of the function f of X star is less than or equal to f of X, right? We say that is a local minimum. We say that X star is a global, or sometimes in the book it's the term is the term that's used is absolute, global or absolute minimum. If this definition is satisfied for all X, it doesn't have to be near X star, but for all X that belongs to the domain, right? Then we say that the point is a global minimum, right? So we have local minimum and we have a global minimum. Okay. So let me draw. Let me make sure. See here. So second. Right. So we call this point here. This is minimum. Okay. And we call, let's say, this point here and this point here. So this is local minimum. And this point here is global minimum. Okay. So you can see that if there is no other point, right, that is less, so this is f, right? This the curve here is f of X. All right. And so this is local minimum as long as X is near X star. So this is X star. This point is X star. So as long as X is near X star, right, f of X star is less than f of X. But here it doesn't matter if X is near or far away, f of X star is always going to be less than or equal to f of X. We call this global minimum and this is local, right? All right, we continue. All right, if f is defined on an interval j, right, and the interval could be written as AB, so when you have an open parentheses here, this is open, it does not include A. This one means that A is included in the domain, in the range, right? Here B is included in the range. A and B here is included in the range, okay? So the definition of global minimum is the same, meaning that instead of R, we can also talk about domain J, right? Domain J. And there's a fact that says that a continuous function has a global minimum and a global maximum on A and B. Any continuous function, no matter what it is, right? It's always going to have a global minimum and a global maximum on a domain that is given by this closed domain A and B. It's a fact in mathematics. Okay. So now let's talk about necessity condition for local minimum. So let f be a scalar function. It takes in x on the domain A and B, and it gives me output on the range R. Be continuously differentiable. So when we say continuously differentiable, it means that the derivative of f or f prime exists and is continuous. All right. Now, the necessary condition for a minimum, local minimum, is that if x star is an interior of the point A and B, is an interior point of the domain A and B, and a local minimum of f, then the derivative of f when substituting by x star, meaning df over dx when substituting by x star is equal to 0. Okay, so the derivative, which is obvious from here, right? So the derivative of f at the point x star is equal to 0, right? Again, here, the rate of change is equal to 0 at these points. All right, so but mathematically speaking, we can show it in a rigorous way by using what's known as the mean value theorem. So the mean value theorem says that f of y minus f of x is equal to f prime of z y minus x, where z is equal to 1 minus beta x plus beta y, and beta is sandwiched between 0 and 1. And okay, so if we can use that mean value theorem, but instead of x and y, we have x star plus t and x star. So basically, we have a perturbation in time, not in space, but in time near when we are in the minimum point. Okay, so if you now use this formula and use this z here, you'll see that you have this. Okay, you can verify that, and so you can add and subtract f prime x star t to this equation here. And then I'm going to define this as O of t. Okay, this term here as O of t. And if you divide this term by t and you take the limit as equal to 0, you can easily see that that term is equal to 0, right? So now replace this with this definition O of t. So end up here with what we have here. And because x star is a local minimum, so it means that even like a deviation in t from f of x star should be larger than or equal to 0. So for sufficient small t, okay? And because t can be positive or negative, sorry, the sign of the right hand side, this sign here of the right hand side, right, will be the sign of f prime t, right? And when the magnitude is sufficiently small. So what I'm trying to say here is that if you divide both sides by t and take the limit as t goes to 0, or when considering t is very small, right, you will see that at the local minimum, right, f star should be equal to 0. F prime of x star is equal to 0. All right, let's now consider an additional assumption, that is, let f be twice continuously differentiable. So both f prime and f double prime exist and are continuous, right? Then, in addition to the necessary condition, we have a sufficient condition, which is if f star is an interior point of the domain, then the derivative of f at x star is equal to 0, and the double derivative of f at x star is positive, then x star is a local minimum. Okay, so this is the necessary and sufficient condition. So we need the first derivative to be equal to 0 and the second derivative to be equal to positive. That implies that we have a local minimum. This fact, I'm sure, is familiar to all of you. You can verify it using Taylor series expansion. I'm going to skip that because it's a well-known fact. Okay. Now let's continue now to the vector form. So up to this slide here, we're talking about scalar valued functions and scalar x, meaning dimension x is equal to 1. How about now x is a vector of dimension n of real numbers, meaning x is a vector of x1, x2 up to xn, where each element of this vector is a scalar value. Okay. Then we need some tools for us to deal with these vectors. The first one is the inner product, what we call inner product. We use this symbol for it, x and y, which is equal to this. So you take the vector x, you do an inner product with y. This is the sum from I is equal to 1 up to n xi yi. And or it's equal to y transpose x is equal to y transpose x. Okay. Now you saw that when we have a scalar value, we use the magnitude sign, right? We know that, right? We know that the magnitude sign is a measure of the amplitude or the magnitude of that signal, right? Well, do we have something similar for a vector? It turns out yes. And for those of you who are not familiar with that, that's the norm. So a norm is a measure of the strength of a vector, right? It specializes to the magnitude when the vector is of dimension 1, right? But if the vector of dimension more than 1, then we need to have a special definition. There are different definitions for the norm, but in this course we are going to consider the Euclidean norm, what's known as the sometimes known as the 2 norm or the Euclidean norm, which is equal to x transpose x, right? Or the sum of all the elements squared, the square root of the sum of all the elements squared. Norms have properties. The three main properties are, first, they are always non-negative, and they are 0 only when x is equal to 0, when the vector is equal to 0. They satisfy the triangle inequality, meaning the norm of x plus y is less than or equal to the norm of x plus the norm of y. Sorry, guys, I have cold, so I'm sorry for coughing. Okay. Keep in mind that x and y are vectors. Um, Let me get water. Give me just 2 minutes, guys. Okay, be back. All right. Sorry about that. Okay, so We have the triangle inequality. And also alpha, which is a scalar, times x, which is a vector. So the norm of that will be the magnitude of alpha times the norm of x. Okay? Any question up to this point? I'm just curious, guys. Who here is not familiar with or did not hear about norms before? Just give me the thumb up if you have never heard of a norm before. So you are all familiar with norms. Excellent. Okay, that's encouraging. That's good. All right, so let me move on. All right, now let me also cover the notion of open set and closed sets. So a set S, which is a subset of real numbers of dimension n, is open for every x that belongs to S, and there is epsilon positive, such that if we are we can define a ball. The center of the ball is x, and the radius of the ball is epsilon, and um, then for all z that belongs to R of n, the norm of z minus x, if that is less than epsilon, then that set is a subset of S, right? We call that a ball of epsilon neighborhood of x. And so let me now just give a sketch of that. A second. So here we are talking about a ball, okay, and here is x, this is epsilon, right? So this is an open set if for any point z, right? So the ball here, why we're talking about ball? Because ball, it covers the fact that z and x are vectors. Okay, so these are not points exactly, but these are vectors, right? I'm trying to make the picture simple here by saying that z here, this point z, is a point, but basically it's a vector. Anyway, if that z is inside that ball, then we say that for all z's that are inside that ball, then that is an open set. Okay. Now, a point B is a boundary point of S if there is epsilon larger than 0, such that a ball contains points in S and points outside S. So what that means is, let's say that this is S, okay? Then a point is a boundary point if it's a ball, right? That has points inside S and points outside S, right? And for a small epsilon, this is like, remember, this is epsilon that is small, right? So this is, in this case here, this is N. In this case here, this is N. Okay, this is the ball, right? A point B is an interior point of S if there is epsilon positive such that the ball is inside S, right? So for example, obviously, so we have S here. If the ball here, so this is N, this is right, this is the ball N, right? We say that this is an interior point. So this is an interior point. This is a boundary point. Let me see here. So it can be any topology, right? I mean, in mathematics, we say that this is a ball, right? So, Alessandro, but it can be any topology. It doesn't have to be a ball, right? It can be any topology. Absolutely, yes. All right. Now, um, partial S is the set of all boundary points of S. So, uh, so, what? So let me use. Let me see here if we can use colors. So this is the boundary points. So this one here is the delta S, right? So this is the boundary of the ball. Boundary is the set of all boundary points of S, right? And this is the interior. And uh, yeah, so this is the boundary point. So this is in. So here, even though I draw it as a big ball, but essentially because epsilon is a small, epsilon can be anything, right? But essentially the assumption here is epsilon is a small. So this is an interior point. Okay. All right. Let's move on. So open and closed sets. An open set contains none of its boundary points. A closed set contains all of its boundary points. So mathematically speaking, we say that a set, for example, this is just an example, the norm of x less than r is just a number. Remember, by the way, guys, I forgot to mention this, which is very important. So the norm takes in, it's a function, it takes in a vector x and it gives us a value that's scalar. So the value here is a scalar, right? So the value of the norm is a number. It gives you, it takes in a vector and and it gives us a non-negative number. Okay, keep that in mind. So the norm of x is less than a number r, okay? In this case, we call this set, right? Which is if it's a uh, if I mean if it's dimension 2, it's a ball, right? And it's an open ball. It's an open set. And if the norm of x is less than or equal to r, then we call that as a closed set. And this is in general for a vector. For a scalar case, we talk about the line of real numbers. And if we have something like this, A and B, that is neither open nor closed. Okay, obviously, because it's closed from the right, but open from the left. Now, interior and closure. The interior of S, we mathematically we use S and a circle, soup circle. So that's S minus its boundary, right? And like for the scalar case, A and B is open. The closure of S, we denoted by S bar, is equal to S plus its boundary, right? And so, for example, A and B is closed. This is for the scalar case. We can also talk about connected domain and bounded. So an open set is connected if every pair of points in S can be joined by an arc lying in S. And so, for example, here we can talk about different. Okay, so we can talk about, for example, here, obviously, if you have something like this, a circle, this is a connected set. Any point can be connected to any other point. If we have a donut, right, this is a connected set. We can connect any point by an arc, right? Also, if you have this shape, for example, right, and this is also connected because this is a connected set. Okay. So a connected set is a set where each 2 points can be connected. If every pair of points in S can be joined by an arc lying in S. Yeah, this is the key here. The arc has to be in S for us to call that set connected. A domain is an open connected set, right? Also known as open space. A set is bounded if there is K positive such that the norm of X is less than or equal to K. For all X, it belongs to the set. Right? So we call that set, if we have less than or equal to K, we call that set bounded set. Right? Because yeah, that's the definition of bounded set. So S is contained in the closed ball of radius K in Rn. Okay. So Alessandro is saying a convex set is any set contains any line, and a connected set is a generalization to any curve. I'm not sure, Alessandro.
As in, like, so a convex set is any set that contains any line connecting 2 points within the set.
Right.
So then the next step or more general is a connected set. Then this is like the most general we can get for connectivity in general.
Yes, I agree. Yes.
Okay.
Yeah.
Great. Thank you.
Okay, let's move on. Okay. Okay, now this we're done with the preliminaries, right? We need to be familiar with norms, connected sets, closed and open sets, bounded sets. We need to know what these means, right? How to deal with vectors. These are things that we need to be familiar with. All right. Now let's talk about static optimization. Again, these are in Athena and Falb 5.2, sections 5.2 to 5.4. So let D be a domain. D could be the whole domain of real numbers. And let's start with the scalar valued function. So first definition, a point X star belongs to D is a local minimum if f of f if there exists epsilon positive such that f of x star is less than or equal to f of x for all x belonging to a ball that is centered around x star with a radius epsilon. Okay. Okay. So this is the definition of a minimum, local minimum. A global minimum, a point x star is a global minimum of f of x star is less than or equal to f of x for all x belongs to the domain. Now, the basic assumption that we're going to make is that f is continuously differentiable, and all partial derivatives with respect to xi, I from 1 up to n, n is the dimension of f, exist and are continuous. Now, the necessary condition for an interior local minimum is that if x star is a local minimum of f and lies in the interior of D, then the partial derivative of f with respect to xi evaluated at x star is equal to 0, right? Equivalently, right, the gradient, we say that the gradient of f evaluated at x star is equal to 0. So this is the extension of the scalar case that I showed you earlier, guys, to the vector case. Okay, and now we have this introduction to the notion of gradient, and gradient is nothing but, so here's the definition of gradient. That is the partial derivative of f with respect to all x elements of x, right? From x1 up to xn, that's the gradient. We use this definition for the column vector, and we use this definition for the row vector or the column transpose, okay? And this is just a discussion of why this is true. I mean, yeah. So I'm going to go over this very quickly. It should be straightforward to see here, but let H define H as a perturbation in time of f at the local minimum x star plus t alpha. Alpha is a vector, right? And a vector of constants, okay? And t, so this is just to make it general. And f has a local minimum at x star implies h has a local minimum at t is equal to 0, okay? And by the chain rule, if you do the chain rule, if you differentiate h, you get this one. And if you substitute at t is equal to 0, right, this t will go away, and then you can write this in a vector form. So this is the gradient times alpha. And so if t is equal to 0 is a local minimum, then by the necessary condition, h prime of 0 is equal to 0, right? And so this is equal to 0. Because alpha is any vector in Rn, any arbitrary vector, right? Then it follows that, of course, it follows that the gradient has to be equal to 0. So this is just a quick discussion of why the gradient has to be equal to 0 as an extension for the vector case for the necessary condition. Now, suppose f is twice continuously differentiable, which means that the partial derivative of f with respect to xi times the partial derivative of f with respect to xj exists and is continuous for every I and j. That's what it means. Then we can also talk about the sufficient condition. So let's go back to the definition of H, right? This is perturbation in time at the local minimum. You differentiate using the chain rule, differentiate again, right? You get this one, and substitute by t is equal to 0. You have this one here. Now you can write this in this vector form. This vector form, we call this matrix a Hessian matrix, which is the partial derivative of f with respect to x1 times partial derivative of f with respect to x1, partial derivative of x with respect to x1 times partial derivative of x with respect to x2, and so on, right? We call this the Hessian matrix. We use this symbol for that, right? Square. And an interesting fact about Hessian matrices is that they are symmetric, meaning this term is equal to that term, and because of that, because the Hessian matrix is symmetric, then all eigenvalues of the Hessian matrix are real. Okay, this is a proven fact. If you have a symmetric matrix, then its eigenvalues are going to be equal, real, not complex. But it's a side point. Okay, now define Q as the Hessian matrix. How are we doing with time here? Second. Still have time. So define Q as the Hessian matrix, right? Then if you go back to here, right? So then you can write this, the definition. Remember, we are dealing with F at X star, okay? We're calling it H, and at times equal to 0. You can write this as here, alpha transpose Q alpha, where Q is the Hessian matrix. All right. Now, if Q is positive definite, right? And because Q is symmetric, this is very important property. Because Q is symmetric, we call this function a quadratic function, right? Quadratic functions has like very interesting properties, and they are used a lot for analysis of functions. Okay, so Q is a symmetric matrix or a function, okay? And alpha is a vector, alpha transpose obviously is a vector, right? Then if as a result of quadratic functions, if Q is positive definite, then that makes alpha transpose Q alpha positive. Now, keep in mind that alpha transpose Q alpha is a scalar. The dimension of alpha transpose Q alpha is a scalar. Okay, keep that in mind. Okay, and so alpha is a vector, Q is a matrix, but if you write it that way, we call that which is coming from here, right? It's the same as this one. Then what we have in our hands is a quadratic function because the Hessian is symmetric. And okay, quadratic functions means that if Q is positive definite, then this function is always going to be positive. Equivalently, if all eigenvalues of Q are positive, then H double prime is going to be equal to 0. H double prime is equal to positive. Okay, I think you see where I'm going with this. Actually, I'm going to here. I'm going to sufficient condition. So the sufficient condition says that if the Hessian, sorry, not Hessian, if the gradient is 0 and the Hessian is positive definite because it's a matrix, then X star is a local minimum. Sufficient and necessary condition. This is necessary condition. This is sufficient condition when F is a vector valued function. Okay, and this discussion, right, agrees with this notion here. All right. Any question? All right, let me now conclude with this example. Investigate the minima of this function here. Let's consider this function. F of x is equal to x1 cubed minus x1 squared x2 plus 2x2 squared. Okay, and over the domain x1 and x2, x1 is always positive and x2 is always positive. Okay, so investigate the minima for this. Okay, so first thing we need to do is, first of all, you notice that this is a scalar, so we don't need the gradient, we don't need the Hessian, it's a scalar, so we do the first derivative and second derivative. Uh, um, um, uh, um, x1 is a scalar. What I meant to say is that x1 is a scalar and x2 is a scalar. Yeah. But x is a vector. But the way I'm writing it here is a scalar. Okay, so keep that in mind. Okay, let's take the partial derivative of f with respect to x1. Take the partial derivative of f with respect to x1. So you have 3x1 squared minus 2x1 x2. Okay, so that's equal to 0. Similarly, take the partial derivative of f with respect to x2. You get that. You get x1 minus x1 squared plus 4x2. From here, you can see that x2 is equal to quarter x1 squared. Take that and substitute it here, right? Then you will, if you substitute it here, okay, so you substitute it here and then take x1 squared as a common factor. You have x1 squared, 6 minus x1 is equal to 0. From there, you can see that x1 and x1 is equal to 0 and x1 is equal to 6 are what's known as the critical points, right? But now you need to check the domain, right? 0. Okay, so once you have x1 and this, you can see what's the associated or the related x2, right? By substituting back by using the equations, right? By using this equation, for example, right? So when x1 is equal to 0, obviously x2 is equal to 0. And when x1 is equal to 6, yeah, so you have 36 over 4, that is 9. So you have 9, 6 and 9 and 0 and 0. Only 6 and 9 belongs to the domain, right? 0 and 0 does not belong to this domain. So only 6 and 9 belongs to this domain. All right, so I think I misspoke. I said we don't need the gradient and Hessian. We do, basically, because we have two-dimensional system. Okay. Okay, so now from the necessary condition, we find the points, the critical points. Yeah, it's a vector, Anas. Yes, I misspoke. So, x is a vector. X is a vector of two dimension, x1 and x2. Okay. Okay, let's find the Hessian. So partial squared f over partial x1 squared, partial squared f over partial x1, partial x2, partial squared f partial x2, partial x1, partial squared f partial x2 squared. So if you do that, you'll get this matrix. You can see that the Hessian is symmetric. You see minus 2x1 here and minus 2x1 there, right? Okay, so yeah, this is the side note that says because D is an open set, of course we don't consider the boundary points. The boundary points of this domain is obviously the 0 and 0, so we don't consider it. So we evaluate the Hessian as 6 at 6 and 9. Right, so if you do that, so you plug in 6 and 9 here, this is the Hessian matrix. We call that Q, right? Now, according to this sufficient condition, we need the Hessian to be positive definite. For a positive definite, then there is a way to see whether a matrix is positive definite or not by looking at the leading principal minors. The leading principal minors need to be positive. For a 2 by 2 matrix, the leading principal minors are 8. This element here, 18, and the determinant of this matrix. You can look up how to determine whether a matrix is positive definite or not. And I believe you can also find it in the background notes I uploaded in Canvas, or a quick search in Google. You can find how to find a matrix, whether it's positive definite or not. So for 2 by 2 matrix, you look at this element and the determinant of the matrix. So this element is 18, so it's positive. The determinant is minus 72. So so Q is not positive definite, right? So the second order sufficient test does not apply. So it's not conclusive. Okay, so it's not conclusive. So we don't know. That's the key here. We don't know. So 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 what I mean by we don't know here, we don't know whether it's maximum or minimum. But if because it's not positive definite, right? So we can, another way to do it is if you take Q and you take alpha as 1 and 1, for example, alpha can be anything, right? If you take it as 1 and 1, then alpha transpose Q alpha is -2, so that's negative. So because it's not positive definite, right? It's not a local minimum. We can say that it's not local minimum, but beyond that, we don't know. That's the key. So I'm going to stop here and I'm going to take it from here next time. Okay. Any question before I let you go, guys? All right. See you on Wednesday, guys. Thank you very much.
Thank you.
Thank you.